Welcome to Chapter 6, Permutations and Combinations. We'll learn fundamental counting techniques to determine the number of ways to arrange and select objects without actually listing them. These techniques have practical applications like figuring out lock combinations, passwords, and signals. This branch of mathematics was developed by Jacob Bernoulli in the 17th century. The fundamental principle of counting is simple but powerful. If one event can occur in m ways and another event can occur in n ways, then both events together can occur in m times n ways. For example, if you have 3 pants and 2 shirts, you can create 3 times 2 equals 6 different outfits. This is also called the multiplication principle. We can extend this principle to more events. For 3 events occurring in m and p ways respectively, the total is m times n times p. For example, choosing from 2 school bags, 3 tiffin boxes, and 2 water bottles gives 2 times 3 times 2 equals 12 different combinations. For k events, simply multiply all the possibilities together. The counting principle has many applications. We can find the number of words formed from letters, the number of signals from flags, the number of possible outcomes in experiments, and the number of arrangements of objects. Anytime you need to count possibilities without listing them all, this principle helps. Let's work through an example. How many 4-letter words can we form from the letters of rows without repetition? The first position has 4 choices, the second has 3 remaining choices, the third has 2, and the last has 1. By the multiplication principle, 4 times 3 times 2 times 1 equals 24 different words. A permutation is an arrangement in a definite order. The key point is that order matters. ABC is different from BAC. We denote the number of permutations of n objects taken r at a time as npr. For example, arranging 3 people in a line from a group of 5 is a permutation. The permutation formula is npr equals m's n minus n minus 2 all the way to nr plus 1. This counts ways to arrange r items. The first choice has n from m n options, the second has n minus 1, and so on. For example, 5p3 equals 5 times 4 times 3 equals 60 arrangements. Factorial notation makes formulas cleaner. N factorial, written n, equals n times n1 times n2, all the way down to 2 times 1. We read this as n factorial. By definition, 0 factorial equals 1. An important property, n factorial equals n times n1 factorial. Using factorials, the permutation formula becomes np equals n factorial divided by n minus r factorial. For example, 5p3 equals 5 factorial divided by 2 factorial, which is 120 divided by 2, giving 60. When r equals n, we get npn equals n factorial, arranging all n objects. When repetition is allowed, each position has n choices, giving n to the power r total arrangements. For example, forming 3-digit numbers from digits 1 through 5. With repetition, we get 5 cubed equals 125 numbers. Without repetition, we get 5p3 equals 60 numbers. The difference is significant. A combination is a selection where order does not matter. ABC and BAC are the same combination because they contain the same elements. We denote combinations as NCR or C of NR. Choosing 3 people from a group of 5 for a committee is a combination. The order of selection doesn't matter. The combination formula is NCR equals n factorial divided by r factorial times nr factorial. The relationship with permutations, NCR equals NPR divided by r factorial. For example, 5c3 equals 5 factorial divided by 3 factorial times 2 factorial, which equals 10 ways to choose 3 from 5. Combinations have important properties. The symmetry property, NCR equals NCNR, also equals NCN equals 1. Pascal's identity states that NCR plus NCR minus 1 equals NCR. These properties are fundamental to the binomial theorem and appear throughout probability theory. The key difference, permutations count arrangements where order matters. Combinations count selections where order doesn't matter. The relationship is NPR equals NSAR times r factorial. Think of it as first choose r items, combination, then arrange them, r factorial ways. Here are practical examples to distinguish them. Arranging books on a shelf, permutation, order matters. Selecting committee members, combination, order doesn't matter. Forming words from letters, permutation. Choosing cards from a deck, combination. Always ask, does changing the order create a different outcome? When objects are identical, we adjust our counting. For n objects, where p are identical, The number of distinct arrangements is n factorial divided by p factorial. For example, arrangements of Mississippi, we divide by factorials of the counts of each repeated letter. The word has 11 letters with various repetitions. Circular permutations count arrangements in a circle. For n objects arranged in a circle, the number is n1 factorial. Why? Because rotating the circle doesn't create a new arrangement. The trick? Fix one object in place, then arrange the remaining n-1 objects. Real-life applications are everywhere. Password security depends on counting possible combinations. Team selections use combinations. Tournament scheduling uses permutations. Probability calculations frequently involve both. These concepts are essential in computer science, statistics, and operations research. Watch out for common mistakes. Don't confuse permutations with combinations. Always check if order matters. When objects repeat, remember to divide by the appropriate factorials. Read problems carefully for restrictions. Make sure you're applying the fundamental principle correctly to each situation. Here are the key formulas to memorize. NPR equals n factorial divided by nr factorial for permutations. NCR equals n factorial divided by r factorial times nr factorial for combinations. With repetition allowed, use n to the power r. For circular arrangements, use NE1 factorial. When solving problems, first identify whether order matters. That tells you permutation or combination. Check if repetition is allowed. Look for special restrictions like must include or cannot be together. Then apply the appropriate formula and calculate carefully. Here's a committee selection example. Select 3 people from 5 men and 4 women with exactly 2 men and 1 woman. Choose 2 men from 5, that's 5C2 equals 10 ways. Choose 1 woman from 4, that's 4C1 equals 4 ways. Total, 10 times 4 equals 40 ways. This is a combination problem. Let's arrange 5 different books on a shelf where 2 particular books must stay together. Treat those 2 books as one unit. Now we have 4 items to arrange. 4 factorial equals 24 ways. But the 2 books can be arranged among themselves in 2 factorial equals 2 ways. Total, 24 times 2 equals 48 arrangements. Pascal's triangle is deeply connected to combinations. The values of NCR form the triangle's entries. Each entry is the sum of the 2 entries above it. This appears in binomial expansion coefficients. The triangle provides a quick way to find combination values without calculating factorials. In this chapter, we learned the fundamental principle of counting. Multiply possibilities for sequential events. Permutations count arrangements where order matters, using NPR equals n factorial over nr factorial. Combinations count selections where order doesn't matter, using NCR equals n factorial over r factorial times nr factorial. Factorial notation simplifies these expressions. These concepts have countless real-world applications. Thank you for joining Chapter 6 on permutations and combinations.